So we're going to number 3 now, Pajarito Powder. Please welcome Tom Stevenson.
Thanks, Dane. Good morning, everyone. I'd like to talk to you a little bit about a small company based in Albuquerque, New Mexico, that makes a small product that has the potential to have a very large impact on a significant industry. I don't think I really need to tell this group that energy is at the core of everything we do in our lives. It's had a dramatic effect on improving standard of living. It's had a dramatic effect on technology advancements. It's had a dramatic effect on mobility, the mobility that allows all of us to be here today, to come from thousands of miles away to gather here in Savannah, Georgia. But we need to be able to create a lot more energy, because it's that energy use that around the world has driven income. The best countries, the most established, successful, richest countries in the world are the ones that have access to energy usage. And that's continued to be the case over many, many years. But the problem is that energy production, as it's done today, is based on a scarce resource. And that scarce resource creates a disparity in wealth in nations. If you look at the 12 richest nations in the world, half of them derive the vast majority of their wealth from the fact that they have access to a scarce resource, the fossil fuels that are at the core of producing energy today. So even beyond the climate change issues, even beyond the other impacts that happen in our world, if we're going to change the economics and create better sustainability around the world, we've got to ultimately change that equation. So when you talk about renewable energy production, when you talk about energy storage and energy portability, it impacts a number of the UN sustainability goals. But I would actually argue that it goes further than that, because the ability of nations around the world to be able to create and then store and move energy on their own has a much broader reaching effect. Now, if you drill down into one particular segment of how energy gets used and talk about transportation, the climate impacts are dramatic. In the United States, the transportation industry is responsible for 28% of the greenhouse gas emissions, and worldwide, that number is 14%. And transportation presents a particular problem because of this need for energy portability and energy storage. The solution, of course, from a mobility standpoint, is that it's time for the internal combustion engine to go. And all around the world, we're seeing policy initiatives that are beginning to change the landscape of how mobility in particular is impacted by the energy industry. Places like the United Kingdom, France, Norway, China, California. California is not a country, but sometimes. And we're at this point where, for the first time, countries are actually starting to establish sunsets for when they're going to allow the use of the internal combustion engine. But there remains a real problem, and it's particularly acute when you talk about the transportation industry. Because renewables, the same issues that we understand to be issues around renewables when they apply to grid, are that much more acute when you start to talk about transportation. What do you do in terms of being able to take that energy and store it and be able to move it around? So for the purposes of our story and for the purposes of our company, enter our hero, hydrogen. And for those of you who happen to be chemistry nerds, I would wish you a happy Hydrogen Day. The atomic mass of hydrogen, of course, is 1.008. And so the marketing folks at the Fuel Cell and Hydrogen Energy Association came up with the idea that October 8th, the 8th day of the 10th month, 10/008, should be National Hydrogen Day. So happy National Hydrogen Day to everybody. That's not why I started Pajarito Powder. I started Pajarito Powder because we need a solution for energy storage and energy portability that's dependent on hydrogen and that has the right kind of economics to ultimately be successful. So as I was growing up as a kid, my father's a physicist, my mother's an electrical engineer. I loved physics, I loved space, one of the early uses of the fuel cells. But where my real passion lay was not so much in the science, and where my capability lied, not so much in the science. And my quantum mechanics professor could certainly agree with that. But what I was really interested in was the opportunity to take a technology and apply it to a real need, to find a solution. And so what I've been doing for my career is been working as an entrepreneur and as an investor to do early stage technology companies and bring these really fascinating technology and energy solutions into the marketplace in a way in which they can start to impact people's lives. And one of the companies that I worked on, which is what really got me excited about fuel cells, was a company where we were doing, that was also based in Albuquerque, New Mexico, where we were doing hydrogen reforming. And we sold that company to a fuel cell firm in the United Kingdom about 15 years ago, a company called Intelligent Energy. And Intelligent Energy created one of the first fuel cell powered motorbikes, which is called the Envy bike, and that's a picture of it there. Interestingly enough, when they first introduced this, all the forum boards spent much more time talking about whether a silent propulsion system was better or worse than loud pipes save lives than the fact that it was being run on a totally renewable resource. But nonetheless, we had for the first time a fuel cell vehicle. But what I realized at that point, and this isn't, a great insight, because others have had it too, is that at the core of the fuel cell, the catalytic materials that are necessary to make the chemical reaction work are too expensive. If you pull apart a fuel cell and you look at what drives the electrochemical reaction that combines hydrogen from a tank and oxygen from the air to produce the electricity, you need a catalyst to make the reaction go fast enough, and that catalyst today is made of platinum. That platinum is expensive, and it doesn't scale very well. And so I went out and watched and waited to see what would happen in the technology developments around alternative catalytic products. And in late 2011, I had a conversation with Dr. Piotr Zeleny from Los Alamos National Laboratories, who would become the chairman of our technical advisory board. And this was a conversation that certainly changed the course of my career and my life. And from that, started in 2012, a few months later, to recruit the team that would become the core of Pajarito Powder. This is Barzu Levy, our CTO and president, next to me, Dr. Alexey Serov, who's our chief scientist, and then Dr. Zeleny, who's the chairman of our technical advisory board. And so we built this team in 2012 to start working more critically on the problem for what we actually create, which is catalysts for fuel cells. Platinum works great if you don't care about the cost. So if you're going to the moon, you're going to put a lot of platinum in there. And if I'm going to the moon, I want a lot of platinum in there because it's a great catalyst and it still is the best performing catalyst in the world. But if you want to make cars, if you want to make ships, if you want to make trains, if you want to make planes, then you have to start to look at the trade-offs between cost and performance. And the US Department of Energy does a study every year where they look primarily at automobiles and say, what would the breakdown of a fuel cell cost if we were making a significant number of them? 500,000 cars a year is typically the number that they use. And at that point, almost half of the total cost of the fuel cell is in the catalyst. So you're not going to get cheaper fuel cells unless you can get cheaper catalysts. Now again, we're not the only ones who understand this. Other companies do as well. And in the last half of the last decade, the fuel cell industry did a tremendous job in cutting out the cost of the fuel cell, primarily by reducing the amount of platinum that went in. But over the course of the last 7 or 8 years, they've basically been stuck, and the little advantages that have come about because platinum is right now today at historically low prices. Obviously, if the demand goes up, the price of the platinum is going to go up, and we're not going to see those same effects going forward. So what we've done is we've developed a catalyst product. We make a powder, and that catalyst powder has the ability to deal with the biggest issue associated with fuel cells, and that is to improve performance and improve durability at a lower loading of platinum. Basically, we can get the same fuel cell and the same fuel cell performance for roughly half the platinum that's been in fuel cells today. And that's at the core of our value proposition to our customers. We do that through a proprietary manufacturing process that we've licensed from the University of New Mexico, from Los Alamos National Laboratories, and from the Institut National de Recherche Scientifique in Montreal, Canada, called Veripor, which allows us to produce a variety of different products customized for the specific needs of our customers. It's an easily scalable process that has the ability to reduce by an order of magnitude at large scale the overall cost of the materials that we're producing, will allow us to cover that gap that currently exists in getting to economic viability for fuel cells. We've just recently started to move into electrolyzer catalysts as well. We're much newer at this part of the business, but the electrolyzers, which are the use of water and electricity to produce hydrogen have the same needs for inexpensive catalysts as exist in the fuel cell. And so ultimately we want to be able to provide electric catalyst solutions that will handle the entire life cycle that covers the production of hydrogen in the form of electrolysis and then ultimately the use of hydrogen in the case of fuel cells. We've had good success. We started the company 6 years ago. We have shipped to customers on 5 continents. We are still missing Australia, so for our friends here in the room from Australia, we would be delighted to add the 6th populated continent onto our list. But more importantly, we've been engaged with just about every automaker outside of China who has a significant fuel cell program to evaluate our product and to include them in next generation products. We've been working with academic customers, we've been working with commercial customers, fuel cell stack manufacturers, component manufacturers, and we've seen a tremendous take-up in our materials over the course of the last couple of years in particular. I'd like to talk about why I started the company, but ultimately it's our team who's been responsible for doing it. They don't actually let me touch the product until they've put it in the bottle, but we've got a dedicated and passionate team of 12 people in total who are working primarily at our facility in Albuquerque, New Mexico to build out our capabilities. We currently have what would be considered a pilot scale plant, which is capable of producing about 350 kilograms a year. That's enough for example, about 10,000 cars. But I wanted to highlight one individual in particular in the lower right-hand corner, Dr. J. Byron McCormick, because he's one of the founding fathers of automotive fuel cells. He was at Los Alamos National Labs and started their program there, and then spent 30 years of his career building up the fuel cell program at General Motors and running their $350 million budget before his retirement in 2009. And he helps to give us our adult supervision, if you will. So I would be remiss to not take a moment and talk about the other primary source of energy storage that is prevalent in the marketplace today, and that's batteries. And we love batteries because batteries and fuel cells work together as very strong complements to address different parts of the duty cycle and distance cycle that are required to be able to really bring electric mobility to the world. So if you need a short distance, a light load, if you want rapid acceleration and very high power density, what you want is a battery. But if you need to go a longer distance, if you want to build a truck, if you want to build a train, if you want to build a ship, you're going to need to go to a fuel cell to handle the greater energy density that can ultimately come from being able to store the fuel on board in the form of compressed hydrogen. And so these two go together very critically to be able to provide a full electric mobility solution that's going to be necessary if we're ultimately going to move off of the internal combustion engine. There are products out in the marketplace today. There are passenger cars in California, in Europe, in Asia that have been introduced by Toyota, by Honda, by Hyundai. There are forklifts. There are now projects going on where there are Class 8 trucks that are rolling down the highways, particularly the ports of Long Beach and Los Angeles, trains, and starting to have announced products for the ocean as well. And I haven't talked much about the ocean, and that's because most of our experience to date has been working on land with the automotive companies. But there are a variety of projects in various different states that are going on. This is the Energy Observer, which uses hydrogen fuel cells and electrolysis so that they can take their excess renewable energy in the form of solar and wind when it's generated, create hydrogen, store it, and then use fuel cells so that they've got propulsion at night when they're becalmed. So from a more industrial application, the EU is working on the Miranda project to introduce the fuel cell ship for longer distance shipping. Several of the cruise companies, including Viking for their river cruises, and then Caribbean have also announced the intention to start to put fuel cells into their systems, initially for shore power and then ultimately for primary propulsion. There's a ferry system that's being built that's supposed to be introduced for the San Francisco Bay Area in California in the middle of 2019 that will be hydrogen powered and completely emissions free. And so this is all leading us to why we're here at Ocean Exchange, because as I already said, our experience has been primarily around doing fuel cells for land-based applications. Been working with the automobile industry. We've been working with something called combined heat and power. But there's great opportunity that exists. And so for us, what we're really excited about is for the networking, even more than the prize. It's to be able to be here to meet people and understand better what's going on in the maritime world. And we like the prize. And if we were so honored to be selected for the Orsil Award, what we would do with it is two things in particular. We would continue our work on our completely precious metal-free catalysts that have no platinum in it whatsoever. These are applications or products that have not really been well suited for automobiles, but we think that they have great potential for maritime applications, and we'd like to put more work against those. And then for our business, not our technology, but our business, it's always been driven by customer discovery. And what we want to be able to do is we want to be able to engage the leaders in maritime fuel cell activity to better understand what the specific needs are so we can continue to tailor our products and build the solutions that will help to drive what has been a successful set of implementations on land to ultimately broaden our scope and cover the other 70% of the world's surface. Thank you very much.
Great, Tom. Thank you.
Thank you.
So, any questions? I think
Surely you have one.
I do. I think that it's really interesting. What is the weight of a fuel cell versus the weight of a battery of comparable power? 'Cause
Right.
That's a big.
So the mass is, it depends a little bit on how the fuel cell is constructed, but that's one of its advantages, particularly when you start to talk about longer distances, is that batteries are heavy if you start to need to add batteries going on. So I can't give you a perfect mathematical answer for it, because the real answer is it depends.
It depends.
All right.
Yeah.
But I think the sense is that if you talk about short-range passenger cars, then the trade-offs of weight and power density actually work fairly well in favor of batteries. As you start to talk about longer ranges, when you talk about long-distance trucks, all you have to do is add a bigger hydrogen tank. And so that becomes much more of a benefit when you start to talk about fuel cells.
Got it. Roger.
Thank you for the presentation. I have many questions, but I'll focus on just two. First is a general question. How much energy can you get out of one fuel cell? Because I'm thinking, how many fuel cells would we need to run a ship? And the second is a lot more specific, and that's the Orsil Award is for our operations. We're not a container carrier, not a bulker, we're ro-ro only.
Right.
And that raises a real issue with where do you put the tank? And the problem we have with tanks is for hydrogen is the same as it is for LNG. It's right in the way of where cargo operations would be. So the vessel architecture has raised particular challenges. So I'd like you to address that point as well, please.
So the question about how large a fuel cell stack you can make is that they're modular. So a fuel cell is a stack of individual cells, and you can get more energy out of a fuel cell either by making each individual cell larger, or more typically by stacking a larger number of cells into a particular stack. So the automotive applications, the sort of car engine, if you will, the fuel cell stack, runs about 100 kilowatts. And remember, our knowledge in the maritime industry is still much more limited, but you know, my understanding is, and obviously it depends a lot on the size of the ship, you know, but you would certainly need something that would be on the order of 100 times the size of that. And so would you put in 100 fuel cell stacks? No. What you'd do is you would look to build bigger cells ultimately and create a larger set of stacks of them, and then you would have redundancy, and so you'd have multiple systems that are in there. And that modular approach is similar to what the automobile industry is doing. For the Class 8 tractor trailers that they're doing on the road, they're basically combining two individual stacks. And so the short answer on the size that you can get to is that they're modular, and you just keep adding fuel cells, and you can get to sort of whatever engine capacity that you need. The question about the storage of the hydrogen is an interesting one. And you know, because we're component manufacturers, and we've been focusing on what can get the maximum energy density out of a particular square centimeter of fuel cell. And that's really where the catalyst comes in. And we're not systems people, and so we don't spend a lot of time on the tanks. We don't spend any time on the tanks or the systems. And so I'm not well qualified to really speak to that. But I do know that within the industry, there are discussions about trying to do liquefied hydrogen, which would improve the overall density and therefore bring down the volumetric requirements. But thus far, certainly and I think that for fleet applications, in maritime or others, then I think that things like liquid hydrogen become much more realistic. What's been really interesting is that what has driven, if you'll forgive the pun on this, in this industry has been the automobile companies for the passenger car application. And you're not going to fill up cars with liquid hydrogen. They're already a little nervous about filling up with compressed hydrogen because it's a slight change from what we do currently. But they've worked all those systems out and it's working just fine. And so I think when you start to talk about building for a large vessel, you can either go to much higher pressures because you can build more substantial pressure vessels, or you can start to talk about liquefied hydrogen. Beyond that, I wouldn't want to comment because, as I say, that's a systems consideration that's a little beyond the level that we work at.
Okay, thank you.
Sure.
Over here?
You might have answered part of the question there, and then you might have mentioned it earlier, but just want to make sure I didn't miss it. So you mentioned the Ocean Observer, Maritime Observer. Anyway, I was wondering, is there a greater benefit at sea versus on cars? And maybe the liquefied hydrogen was part of that answer, plus maybe generating it and storing it at sea. But I know, the ocean is very friendly for fuel cells, right? So.
Well, yeah. So we think that we think that there's some real opportunities because one of the things about passenger cars in particular is that they have very, very tight constraints around what the size of the fuel cell stack has to be relative to the amount of cargo that gets carried. And that our sense is that as you scale up to larger applications, then those challenges end up being reduced. And so, we feel very strongly that there's going to be good applications for fuel cells for maritime. In particular, when you start to again, you start with the assumption that we need to move to emissions-free solutions. And battery solutions, we don't believe are going to work particularly for large-scale maritime. So for small scale, for pleasure craft, it's again a little bit of a different thing because you get great acceleration. And so if it's a speedboat that you're concerned about, then the speed racing is going to get done by batteries because they have the instant acceleration and they'll always beat fuel cells for that. But I don't want my container ships to accelerate really fast.
There's a lot of little vessels that need long endurance. So
but and they would be very well suited as well.
Yeah.
But to my point, I'd love to have this conversation further. That this is something that we're still learning a lot more about the maritime applications for fuel cells. So thank you.
Over here, Ann.
So we do a lot of work at Port of LA and Long Beach, and so of course pollution of ships at berth is an issue, and so of course you can have the cold ironing, the plug-in solution. There's also barge-based solution where it's basically a sock on a stack to capture the emissions. What do you see as an opportunity? You mentioned shore power. Can you expand a bit on that, on your thinking or where you've gone thus far in thinking of that as a potential market opportunity?
So I think that for us, the shore power, in the United States, a lot of that will have the ability to connect into the grid and therefore have all of the benefits, the load leveling from the grid. But for specific needs for ships, if you're going to need to put down a dedicated power supply for ships that are coming into berth, then there is great opportunity for fuel cells. Depending on what the base load need is, there are different technologies within fuel cells. And there are ones, for example, if you need to run a large factory, there's a different technology called a solid oxide fuel cell that's more prevalent and would be well suited for that. But if you need to turn it on and off, if you have a lot of differences in your loads, then it would be much more suited to the types of fuel cells that we're working on. Early on, I think the work that we've seen that's been going on in the Port of LA and Long Beach has been much more on the shore side, where you're using fuel cell powered forklifts, you're using fuel cell powered drayage trucks, and to be able to move the goods ultimately to their next point as they're continuing their journey here in the United States. And I suspect that that will start sooner because it's a little bit more tied into the land-based activities that have had significant investment already. But there's no question that the port activity is very significant. And we have not, the short answer is we have not sized out the market opportunity for shore power yet. So I can't give you a number associated with that.
Ray?
So, simple question. How do you see your product and your business model 10 years from now? And let me give you some context for the question. So, we look at these new technologies for how we can use them in our company, but also as we can position ourselves for products and services that we offer to our customers, primarily in the auto industry. And we look at Nikola with the compressed hydrogen on the trucks versus Tesla with the electricity.
Right.
And I agree with you. Acceleration on a truck is not the deal. It's about range. But if you look at lithium-ion technology, and then it goes to lithium-nickel-ion, and then it eventually gets to solid state, and the cost of the kilowatt hours come down, so there's price parity with the internal combustion engine, and range anxiety is gone, then how do you see the fuel cells? It's going to be a little bit of a Betamax VHS kind of decision.
Well,
if batteries prevail, how do you see your business model in 10 years?
well, so, I mean, fundamentally, we don't believe that the batteries will prevail across all applications. All right, we believe that for longer distance transportation and heavier loads, the fuel cells will always have better economics because of the ability to take more energy along with you. And, you know, the best estimates I've seen, so Tesla's announcements about the big rig truck are a great example of this, right? I mean, they're talking about being able to get 500 miles and then doing a recharging of about an hour on something called a mega charger. And the Financial Times did some analysis and said adding a single mega charger would be the equivalent of adding 4,000 homes to the grid. And so you start to get into grid considerations as well, which is one of the things that the automobile companies have been looking at a great deal. So, you know, we believe that ultimately it's going to be a combination of fuel cells and batteries. It's not unlike the fact that diesel is so prevalent. So in the United States, right, diesel is not very prevalent for passenger cars, but it's still the predominant fuel source for long distance travel, and so the fuel cells have the opportunity to replace that. The other thing that's great about any sort of fleet operations is it addresses the hydrogen infrastructure issue, because if you have a fleet, you have controlled sets of points where you're going to be refueling, and you can sort of control that and build that out exactly like Nikola is doing. To your question about the business model, though, we make powder, and that is our fundamental goal. Our expectation is that we will be rolled up into a larger company within the next 3 to 5 years. Because ultimately what's going to happen is that right now, if you look at the supply chain associated with the components associated with fuel cells, again, I keep coming back to the automotive industry because they've made the biggest investments in this industry to date and in this technology to date. And the automobile companies are pretty much vertically integrated, but their expectation, and we've learned this from Dr. McCormick, our board member, that, you know, that they will start to split that out, just as they've done with the conventional supply chain for production of internal combustion engines. And so where we're going to fit is a part of providing a proprietary solution into someone who makes one of those components that ultimately leads up to a fuel cell car. So we don't anticipate doing that vertical integration ourselves. We anticipate ultimately that we would be a better fit to provide the proprietary piece to someone who's either making MEAs or making full stacks for someone that ultimately is doing a full transportation solution.
Kathy, did you have a question?
Ray jumped in front of me. So what happens to the end product? We have a catalyst, and then what happens once the goodie is gotten out of the battery? Is there a byproduct to this process? And if so, what happens to it?
Okay, so I'm not sure if you're asking about the manufacturing of our product or what the vehicle. So
With the powder.
The powder itself. So the powder is not consumed like the fuel is, and so it's a component of the fuel cell stack, and then ultimately will have the same sort of lifetime as the rest of the fuel cell stack. Depending on the amount of precious metal that's in the stack, there's some discussions about doing recycling, just as there have been with catalytic converters. The actual materials themselves are relatively innocuous, so they themselves don't have an environmental impact. They are carbon, but they're a solid form of carbon, and so they don't, they're obviously not doing anything from a greenhouse gas standpoint. So they don't get used up. They'll just remain in the system and ultimately be disposed of or recycled with the rest of the vehicle at the end of life of the fuel cell. Typically, no. You wouldn't, and frankly, our materials are inexpensive enough that that's not the route that you would do. You would instead look at doing some sort of large-scale recycling of the overall vehicle. Okay. So you don't recharge it. You go for the overall life of the vehicle, just like you don't have to, there are components you replace in an internal combustion engine, but it's not like the oil that has to be replenished or replaced. It's more like the engine block that would last the full life of the car.
Let's see if we can get one more question in.
Yep.
Quick question. You may have answered this in your presentation. I might have missed it. Early on in your presentation, you talked about the cost to performance ratio, and you said that the role of the catalyst is upwards towards 50% of the cost of the fuel cell because of the precious metal. I didn't hear the number that the powder reduces that 50% to.
I didn't actually say that. $10 a kilowatt.
It reduces by $10 a kilowatt.
Right. So today, if it's 50 and the target is 30, on a direct basis, we can take $10 a kilowatt out of the.
And how does that
system.
relate to percentage in the total cost?
It's about it would be about 20% of the cost today, and about half of what you need to get to in order to get to economic viability. There are some other indirect benefits as well, potentially, that could actually increase that. But if you just compare it to the cost of the precious metals, it takes out $10 a kilowatt. And
Tom,
with that,
thanks.
Thank you.
Great stuff.